Here's a very short description of why the real and imaginary parts, when we're dealing with a damped harmonic oscillator of this form that has a complex solution, because it ends up with a value of s that's complex from the characteristic polynomial, why a solution of the damped harmonic oscillator, why both the real and imaginary parts of that function also must be solutions. Here's our damped harmonic oscillator, characteristic polynomial s plus ps plus q, s squared plus ps plus q. Pythagorean quadratic formula reveals in some cases that s can be a complex number. It's in our underdamped case, by the way, but we have a complex number for s, and so that means that the solution, e to the st, when we apply Euler's formula, will get a real part and an imaginary part. Since by design we chose a value of s so that this will be a function, so when I take its second derivative, I get s squared, and I take its first derivative, I get an s, so ps, and the function itself is just q times e to the st. When I take this and plug it in, it will equal 0, because s has been chosen to be something that satisfies the characteristic polynomial. But since y of t has a real part and an imaginary part, I could also substitute in to the second derivative y1 plus iy2 in place of the first derivative. That's the derivative instead of y, it's y1 plus y2. And finally, in place of y here, I've just got q times y1, y2. Collecting the real parts, the y1 parts, from the imaginary parts I see here, I left off an I here, I left off an I there. When I collect the real and imaginary parts, the real parts are y1 here, and y1 here. I've got the second derivative of y1 plus p times the first derivative of y1 plus q times y1, and then plus all the terms that had I in them. So the second derivative of y2, first derivative of y2 times p, and then just q times y2. When I collect those together, put a parentheses around all the terms that had i's, I have the statement that this real part plus this imaginary part have to be 0. The only way I'm going to add a little bit more here, I'm going to write that this is 0, yes, but it's also I times 0. It's the complex 0 where both the real and the imaginary part are 0. Well, here's the real part that gets compared to this 0. Here's the imaginary part that gets compared to this 0, saying that this statement equals 0 and that this sum of terms must also equal 0 indicates that the function y1 must be a solution of the damped harmonic oscillator, because its second derivative plus p times its first derivative plus q times y1 equals 0. Similarly, the second derivative of y2 plus p times the derivative of y2 plus q times y2 must be 0, because on the right-hand side there's a 0 imaginary part, and this is the imaginary part. That means that y2 is also a solution of the damped harmonic oscillator. So when we end up in the case where our characteristic polynomial yields a complex number, and we express it, we use Euler's formula, we find our two parts of our complex valued function, we know that we can take the real part and the imaginary part, and we know they're both real valued functions, and use those as the basis for building our general solution. And so that's the approach that we take. We don't carry forth the I. Although this is a perfectly good solution, it's a complex valued function, and we want real valued functions. So that's why we're allowed to pick them off. I hope that helps. Good luck. Bye-bye.